Dear students, today's video lecture will deal with the section 4 of your syllabus, that is derivation languages. We will study this material from Georgery Reeves' book. This is chapter number 10. First, we will work on the operations which can be applied on derivations. So first of all, what is a derivation? As in case of simple languages that we had learned earlier, a language governed by a grammar G can be depicted as a four-tuple. This book has a bit of difference in notations. Let's follow them. I'll tell you whenever there is a change. First component of this four-tuple is Vn. Vn is set of non-terminal symbols. Means earlier we used to call them variables. The second component is Vt, set of terminals. Earlier we used to call them sigma. And then instead of production we have start symbol S. And then in the last F is the set of production rules. So a grammar in this book will be denoted by a four-tuple Vn, set of non-terminals, Vt, set of terminals, start symbol, and production rules. So this grammar has a number of production rules, and on applying these production rules we will start from a particular string and replacement will go on. So let us suppose we start with the first string x naught. Its name is p also, so p is equal to x naught. So after applying some production we will reach at a string x1. After applying another production rule we will reach on, and so on. Ultimately we will reach in the last at xn string. So this last string is also named as q. So this is actually a derivation starting from P and ending at Q. This can be represented by this equation, and as well as it can be represented by derivation graph also, or whatever you call it, derivation tree. So, so the derivation word, hope it is clear to you. This chapter will deal with the languages generated by these derivations. First of all, let us consider the first definition, rewriting system. Rewriting system, as the name indicates, that we are going to rewrite the string after using production rules. So analytically it is represented by R, and it's a two-tuple. First part is V. Here V is combination of union of Vn and Vt. So V is a set of terminals as well as variables. Earlier we used to represent in a different way, but now V is union of Vn and Vt. So Vn containing non-terminals, Vt containing terminals, and after uniting these two sets we get V. So V is a set of terminals, irrespective of that they are V is a set of symbols, irrespective of being terminal or non-terminal, and F is the set of production. So combination of these two components gives you rewriting system. Okay, we can read it. A rewriting system R is a system of V and F, where V is a finite alphabet. Alphabet is symbol, and F is a finite set of ordered pairs. So ordered pairs in this book, a production is earlier we used to write production as P arrow Q, but this time we are showing it as a pair P to Q. So production rule will change this string to this string PQ. So set of alphabets and production rules such that P belongs to V star, and Q belongs to V P belongs to V plus, Q belongs to V star. What is the difference between V star and V plus? V star includes empty string also, but V plus excludes it. So left hand side of the production rule should have at least one symbol, whereas right hand side can be empty also. So grammar rewriting system is given by RG is equal to Vn union Vt F. Right? Hope you understand rewriting system. And you can read it as a convention where G is grammar is used. V is equal to Vn union Vt, means union of non-terminal and terminal symbols is denoted by V in this book, so that Rg is equal to Vf. So this is the rewriting rule, rewriting system. And one more thing I want to mention here, VF. VF is a set of names of the production. Actually, all the productions are represented by some name. We take an example. Suppose you are given this example, G is a grammar, Vn, Vt, S and F. Where Vn is S, A, B, these are the non-terminal symbols, these are the terminal symbols, and these are the productions, S to S, A, B, B to A, B, A to A, B. So every production is given a name. Every production is given a name. For example, this production is given name F1, this production is given the name F2, and this is given F3. So collection of these F1, F2, F3 means names of the production. Just a minute. Collection of names of the production is given this term VF. So the names in VF are often called production names and production labels. Here we are mentioning that a derivation, for example, this notation indicates that we start with P, and after so many productions, implementing so many productions, we reach at Q. So this is indicated by this. But if we follow a rule here that every leftmost variable will be replaced, then it is known as leftmost derivation, and it will be indicated by this P star left Q. Right? So if two you can see, if two graphs which have the same derivation, leftmost derivation, they are known as equivalent. Here they are equivalent if and only if they have the same derivation graph of the leftmost derivation. And if we take leftmost derivation every time, it becomes a standard that whenever derivation is talked about, it is always leftmost derivation. So it is known as canonical derivation. So canonical derivation means standard method used to derive the string. We can apply various operations on the derivations, among which composition and juxtaposition are the two majormost operations. We take them up one by one. First of all, the first definition, let W1 and W2 be two derivations. Now derivation, see, every derivation is indicated in the form of a word. We will talk a little later, but let's take W1 is a derivation graph derivation, and similarly W2 is another derivation. So we can apply operations on these two derivations. So let W1 and W2 be two derivations in the rewriting system R, such that W1 is this. W1 starts from P1 and ends at Q1, and in between it switches from X0 to X1 to X3 up to Xm, and the last replacement is also named Q1. Similarly, W2, we have P2 the starting point and Q2 is the final string, and on the way Y0 is replaced with Y1 and it is replaced with Y2 and so on, and in the last it is replaced with Yn, and this Yn is termed Q2. So now we are having two derivations, W1 and W2. Juxtaposition of W1 with W2 written as W1 cross W2 is the derivation. So it is indicated by this W1 cross W2 colon P1 P2. This means that juxtaposition of W1 and W2. In this we start from the concatenation of both the first strings P1 and P2, and we start replacing first string and the second string from the W2 will be unchanged. For example, x0 y0 is a string in which x0 is replaced by x1, but y0 is not changed at all. Similarly, x1 will be replaced by x2, so it will become x2 y0, x3 y0, x4 y0, and so on, and in the last xm y0. Once we have reached at the last position, last derivation, after that we will replace y0 with next replacement, which is y1. So after this we will have xm y1, and after that we will replace xm with y2, so xm with yn in the last, and this xm yn is also written as q1 q2. So starting from p1 p2 we reach q1 q2. On the way the derivation is done in this way, in this style, and such concatenation style is known as juxtaposition. And juxtaposition is associative but not commutative. So this follows associative property, but commutative property it is not valid. Means juxtaposition of P1 P2 is not equal to juxtaposition of P2 P1. Similarly, we have an identity element. Identity element means if we apply juxtaposition of any string with identity element, it does not change at all. For example, if you apply identity element on x, and after replacement it will be unchanged as x. So identity element also exists. So juxtaposition is associative, juxtaposition is not commutative, juxtaposition contains identity element. Identity element can also be depicted by this juxtaposition of any string, any word with any derivation with identity element, or any word with identity element on the right hand side. This does not change it at all. Second operation on derivation is composition. So let us start studying the definition. Let W1 and W2 be two derivations in rewriting system R such that W1 and W2 are defined as this, starting from P and going through these steps and reaching Q2, and similarly W2 starts from Q and reaches, after these steps, reaches at T, right? So composition of W2 and W1 is written as this. So first derivation is written on the right hand side, and then this symbol of a small circle, and the second derivation on the left hand side. So this indicates composition of W1 and W2. So it is defined as we start from P and after applying W1 derivation, we reach at Q, and on reaching Q, the second derivation will be applied to it. So Q will be applied second derivation and we will reach T. So starting from P and at the end point of the first derivation, we start applying the derivation of the second W2 and we will reach at the T. So this is just a sequence of the multiple derivations. Similarly, composition is also associative and composition is also non-commutative, as in case of juxtaposition, and similarly identity element also exists in composition operation also. So it can be indicated composition of identity element on W or composition of W on identity element. This also makes no difference. So this indicates that composition also contains all the three properties, and we have just a minute, we have methods to extend these rules. We will learn them later. Now we come to another definition, derivation word. Derivation word, actually derivation was earlier depicted by a graph. Graphical method was used, but in case of algebraic operations, every time drawing a graph is not advisable. So derivation word is actually a string form of graphs. How to represent a graph? We will take it up with an example. So let's go to the example. Here in this case, G is the grammar we are using. It is having 4 components: Vn, Vt, S and F. Everything is clear to you all. Similarly, V is union of Vn and Vt. Vf is the set of all the production rules. So now if we start with the start symbol F, on this symbol you can apply some suitable production from this set. This production can be applied. So F1 rule, F1 production can be applied to achieve. So this is indicated in the graph as S, and we are applying F1 production and we are getting SAB. So on application of rule F1, we get SAB from S. Similarly, again S can be applied, same production rule F1, and it can yield SAB. So it is written as S on applying production rule F1. It gives SAB. And similarly on this side B can be replaced using this rule. Here notation is not followed. Proper notation is not followed, in which capital letters are indicating terminal non-terminals and small case letters are indicating terminal symbol. It is not followed, so just ignore it. So F1 on B1 on applying F2 rule ekes out ABA. So this is indicated by this. So this is the graphical representation of derivation. This graphical representation is not advisable to be used everywhere in the algebraic form. So here this derivation can also be depicted by this string. Look at it very carefully. S is the start symbol, then we apply production rule F1. On applying production rule F1, we get S, and then S is again applied production rule F1. So S on applying F1 gives you SAB. So if we take we traverse this tree SAB, and after that A. So SABA, and after that you have B. So this B on production of rule F2 gives you ABA. So this derivation is also indicated in the form of a string, which eventually is known as a word. So this word is known as the derivation word. You can label it by some appropriate symbol, for example W1. So W1 is the derivation word. Actually, derivation word is a replacement for the derivation graph. Let's be back on the book. So derivation word, hope you understand it. And similarly, composition and juxtaposition are also applied on derivation words. In addition to it, we have two new terms, two new functions, domain and codomain in picture. So domain means something, a string on application of the derivation you receive. For example, you are finding domain of W. It means some string which on application of derivation yields W. Similarly, we can have codomain of W. Codomain of W means W on derivation or W on application of derivation will yield the string. That string will be known as codomain. So I repeat once again, domain of W is a string which on application of derivation gives you W. And codomain of W is a string which codomain of W is a string which is yielded by application of derivation on W. So domain is basically the previous step of the W, and codomain is the next step of W. So let's read the definition. Let RVF is the rewriting system. As you know, rewriting system contains terminals, variables and production rules. The domain of a word W belonging to V union VF means, what does this mean? V union VF star. V is symbol, terminal or non-terminal, and VF is a production rule, name of the production rule. So this word can contain variable, terminal and some production name. So star means combination of these three elements. So any word W, domain of a word W is written as DOMW, and it is defined inductively as follows. If W belongs to V star, means W contains VT or VN only, no production rule is involved in this case, then domain of W is W itself. And secondly, domain of this string XFQY, this string also contains variable terminals as well as production rule F. So for this, domain is given as XY. So first and the last strings are extracted and they are concatenated. This gives you domain, but it should follow the conditions, whereas domain of XY should be defined. There should the domain of XY should exist, and secondly P to Q should be a production in the production rules set. So domain of finding any string having no production rule is very simple. It's the word itself, and in case F is also involved, then it is XY. But provided domain of XY exists, number one, and number two, there should be a production rule P to Q. Similarly, codomain, finding codomain of a word W, it is written as COD, codomain. CODW is defined inductively as follows. If W belongs to V star, means there is no production rule, then codomain of W is W itself. But if it contains some production name also, F also, then production its codomain is given as codomain of XY. Codomain of XY, but this time condition is that codomain of XY should exist, and secondly P to Q should be a production. Here a little difference between domain and codomain is that we are having FQ, F in front of Q, and here we are having F after P, because this is codomain. So if production P to Q exists and codomain of XY exists, then codomain of XPFY is codomain of XY. This way we can find out domain and codomain of Next, we can extend these the rules to have a larger string. For example, we are having a string containing 3 substrings W1, W2, W3. So finding domain of this larger string is easy now. So first you find domain of the middle word, the domain of the word which is in the middle, and after concatenating it with the W1 and W3 remaining words, find domain of it. Similarly, codomain also can be calculated in the same way. You can have this. Now we come to the language, derivation language. Derivation language is actually a collection of all the derivation words. Let's take the example first, then we will define it. We take the same example. W1 is the word, derivation word. Similarly, these productions can be used in a different way, having different word, a different derivation tree, and that derivation tree will also have an equivalent word. Let us say W2. Similarly, third derivation tree will have word W3 and so on. So collecting all these W1, W2, W3 etc. gives you language, derivation language, and derivation language is written as DR, where R is the rewriting system. Let's be back to the book. Let R VF be a rewriting system. Derivation language of R DR, derivation language is written by DR, is defined inductively as follows. First step is, if W belongs to V star, means W contains only alphabet, variables and terminals, and there is no production rule, then W belongs to the language. W is an element of the set, having the set of the language. Secondly, the string like this, X, F, Q, Y. Observe this string contains a production symbol F also. So if it does not contain a production symbol, then definitely it is a part of the language. But if it contains a production symbol, then it's a part of language if these rules are followed. Of this, number one, first rule is that X, Y also belong to the language, also belong to the derivation language. Secondly, codomain of X and Y also exist. Thirdly, there should be a production P to Q. And fourthly, codomain of X should be having a concatenation of ZP, where Z is V star only, means Z does not contain any production system, production rule, and code means codomain of X does not contain a production rule. So following these conditions, this word can be said to be belonging to the derivation language. And thirdly, nothing else belongs to the derivation language. If these two rules are not followed, then the word is not a part of the language. You have been given an example. The example we have been taking, the similar example. Here we have the word, and domain of the word and codomain of the word can be studied. Now let's switch to the algebraic properties of the fundamental operations. Fundamental operations are juxtaposition, composition, etc. We will work on the algebraic properties of this. First definition is, let W1 and W2 are the derivation words. Hope you clearly understand these derivation words. Let W1 and W2 be in V union VF star. Then the juxtaposition of W1 with W2 written by cross symbol, W1 cross W2, is just the concatenation of these two words, W1 and W2. Right? Nothing extraordinary is being done here. Similarly, we have theorem: if W1 and W2 are in the language, derivation language, then W1 cross W2 also are in the derivation language. Okay, if W1 and W2 are the words contained in the derivation language and you apply juxtaposition on these two words, then the result will also be part of the language. Similarly, we can study composition also. Composition of two derivation trees. It's indicated by an example. Let's take this example. This is the derivation tree, first derivation tree or graph, in which AB. Before going to it, let's discuss the grammar which it is discussing. This is the grammar having F1, F2, F3, F4, F5 and F6, 6 production rules. We will be using these production rules to derive a grammar. For example, F3 is being used there, where AB is replaced with SAB. So AB clubbed using F3 rule changes to SAB. Similarly, again we have AB combination. We can apply the same production rule F3, which changes AB to SAB. So now we have SSAB. Similarly, we can apply production F2. F2 production is S to BA. So this, on applying this production on S, it becomes BA. So this is one derivation tree, derivation graph. This can also be depicted by derivation words, as you can AB, F3, SAB, then F3 again was used, SF, then F2 was used, and we got BAAB. The second derivation tree is, for example, SB. S on application of F2 rule becomes BA. Now we have A and B. A and B on application of rule F3 gives you SAB. And S on application of F2 gives you BA. And AB on application of F3 again gives you SAB. Right? This goes on. Similarly, we are applying BAS F4 rule. F4 rule is BAS replaces with AA. So BAS, on applying F4 rule you get AA. So these two derivations, on composing it, so composition of these two derivations gives you another derivation depicted by this this derivation graph. For example, AB on giving the, on application of S3 gives this, then F2, then so we have clubbed both of the derivations into a single derivation graph. If you watch it carefully, you will observe the usage of both these graphs. So composition gives you composing of two multiple